Our esteemed speaker for today, Dr. Sandeep Kumar, our HOD, all faculty members, and all the students of chemistry department. Global warming is such an issue that no one is unaware of this. And as a science students, we know that greenhouse gases are the main cause of global warming. And carbon dioxide is one of the greenhouse gases. And the scientific community is doing a lot of research on reducing the level of carbon dioxide. And one of the idea about this is to convert the carbon dioxide into useful chemicals. And this is the research area on which our today's speaker, Dr. Nandini Devi, is going to deliver her talk. And before passing the podium to Dr. Nandini Devi, let me introduce her briefly. Dr. Nandini Devi is a scientist in National Chemical Laboratory, Pune, India's one of premier lab in chemistry. She has done her MSc and PhD from IIT Madras, and after completing her PhD, she did her postdoc from Syracuse University, USA, and St. Andrews, UK, as well as Queen's University, UK. And her research interest includes single atom catalysis, structural and electrochemical characterization of structural oxides, nanomaterial for bioapplications, quantum sensing, in situ IR study of CO2 utilization, inorganic hollow fiber catalyst, photocatalysis, and reforming reactions. She has guided 8 students for their PhD, and I'm lucky to be one among them. And currently, more than 10 students are working in her laboratory for their PhD. And she is very enthusiastic and humble lady with very good knowledge of her subject. So with these words, I pass the podium to Dr. Nandini Devi to deliver her talk.
Okay.
Ma'am, please.
Thank you, Atul. Thank you. And I think I also was lucky to have you as a student, my first student for that matter. You know, when you join a new institute, it's always good to have good students. So thank you. And thank you for the introduction. And thank you for all of you for giving me this opportunity to talk to young students about this very, very pressing and very serious matter. Unless this generation takes interest in that and starts working on that, I think we will really lose our planet. That's how serious it is. That's what I believe. And I see the names of all the participants, and I see many girls. So I'm very happy to talk to them because, you know, like as half of the population, or more than that for that matter, I think women will have to take more responsibility and start working in these kind of fields as a manpower itself. So I'm very happy to give this presentation today. And now I will stop my video and I will start the presentation. Yeah. I'm hoping that everybody can see the slides.
Yes, ma'am.
Yeah, okay. So today I will present, even though the title is a bit different. This was it is one of the general titles which I have used for sustainable development. So pollution and alternate fuels come in sustainable development. So in here we will focus more on CO2 utilization and how we can convert that into alternate fuels. So I will give some little bit of introduction on sustainable development, because this is one thing where people seem to be very confused. So there is always a thought that can we have development without pollution? when you look at it, if you take your vehicle out, you are polluting. But then can we live without having a vehicle? Can we walk everywhere? Can we, of course, cycling is a very good habit, but then can we do that sustainably? So this is where the confusion comes, even in young minds also. Maybe if I could talk to them, I would have asked some questions, but we'll restrict that now. What is your idea of development? So this is something which has to be very clear in your mind. So there's a definition for sustainable development. So sustainability means that it should satisfy the need of the present without compromising the capacity of future generations. So it is actually, I would blame my generation, because we are probably utilizing or consuming a lot of resources and not leaving much for our children's or even the students' generation for that matter, right? So because you must have heard that, okay, oil is depleting, gas is depleting. So where are we going to get all these things after some time? So we are really not thinking of future generations, maybe, I don't know, 1,000, 2,000 years down the lane, and we are just consuming it. So that is not a very sustainable way of development. But this is something which you will have to understand. And again, at an end, you can just look through those texts which are given there. So at the environmental level, sustainability prevents nature from being used as an inexhaustible source of resource and ensures its protection and rational use. That is extremely important, even water or electricity for that matter. So we should have a very rational way of using it. It is not that it is available, so let us use it. That should not be the way of, because some point of time it is going to exhaust. So environmental conservation, renewable energy, saving water, which is, for me personally, I think that's one of the most important things which we need to really think about. Sustainable mobility, that we will talk a little bit about that. Innovation in sustainable construction. So our construction, the way of construction is extremely non-sustainable, because we really use up things and we don't reuse that. So we can't really reuse construction waste back into the construction of new buildings. So these kind of things are also, so everything becomes part of a sustainable development. So that is what in that three ring image I have given in the side. So that also shows that you need environmental, social, and economic. Then only everything comes together and forms a sustainable development. So this is something which I would like the young generation to think about when they are using any resource. It doesn't mean that you should not have fun, right? So that is what I always ask whenever I talk to young people. See, I myself cannot live without my smartphone, right? What are the sources we are using in that? How much of plastic? When people say, no, don't use plastic. Can we live really without plastic? From my toe to my head, I am using some or other plastic product. So this is the thing. So you need to have a balance of sustainable, development as well as sustainability. So this is my my appeal to the young generation. And environmental impact of development. Let us have a look. So here, if you look at this pie chart, you see what are the things which are creating pollution. So one is metal mining, but then can we really live without metal mining? We can't. But then can we find out better ways of doing that? Yes, we can. So that is where the research comes in. So this can be it needn't be 47%. I'm sure it can be reduced 10% if we use the right ways of doing it. It may become more expensive, but then that is a way to do it. So because we can't now say that no, if you don't pollute the environment, then it becomes more expensive. So let us not do that. So that is not an excuse or a reason anymore. And if you look at electrical utilities, it is around 13% of the pollution comes from that, which we know because we burn coal. So there's no other way to get electricity. If you are not in a very water-rich area, then you don't have a big dam to supply electricity through hydroelectric ways. Then you have to burn coal. So I'm from Maharashtra. So Maharashtra has one of the biggest number of coal thermal power plants. So I can't complain because my electricity is very stable. So I can't really complain about that. But then can we produce this electricity even from coal by better ways of burning coal? There are better ways of doing it. But my electricity charges may go from, let us say, 4 rupees per unit to 7 rupees per unit. But then I should be willing to pay that as a citizen for reducing the environmental pollution. So that is where the compromise comes. And chemicals also is not, but then without chemicals, we really cannot live. So everything together, it's quite polluted. And if you look at one of the things, I think this is an older data. I'm sure this Delhi has, gone past all these things now. I think recently, I'm sure you all read newspaper, if not newspaper, something in your Google must be telling you, sending you some links or something, some alerts of news. So you must have heard that the most part of Delhi, the air pollution indicators, those machines which were there, they were supposed to go only till 999. Afterwards, it cannot, and they went beyond that. So that is that is a very sad situation for a country like India, which is not we can't call ourselves a very poor and then very poor country or anything. We have enough resources to have a good living. We have enough resources. We have enough brain to have innovation and then make technologies. We cannot have that excuse that no, we are too poor or anything. We should be living a much better life, in my view, in India. So Delhi has a very, very different reasons, but then a lot of other countries also are part of it. Of course, our friend Pakistan also is there, very much behind us. But Doha is actually a pretty very rich country. It can do better. But I think it is I have visited that. It is like because it is a desert. It is a desert city. So they produce a lot of water by desalination, and they burn their gas. Maybe one of the reasons why. And it is a very dusty place. So maybe that is one of the reasons. Otherwise, it is full India. And in India, like I showed here, let us forget about this part. This is and it's not my expertise also, and I'm sure mining is getting better with foreign investments and all that. I think technologies are getting better. Hopefully, we'll be able to reduce this. But my expertise or my interest lies in this oil, coal, and their use is what I'm interested in. How do we do that, and why are we using oil? And then how does it contribute so drastically is what I will. So before that, I will just give a brief introduction. It's a very interesting story. So I try to tell this to the younger students because it's a very interesting. So how did we start using this petroleum? So it's a nice thing. This is one of the oldest petroleum. I would call it mine those days. So actually, when they dug up this oil, they call it rock oil because they got it from rock, literally from the ground, right? And you won't believe this first use of it or first marketing of oil did not happen for burning. And that fellow, one Kerr, Samuel Kerr, is a very, I feel that he was one of the cleverest people around. So he started selling it as natural remedy for skin diseases, and then he even started selling it for stomach problems. So I think he was really forcing people to drink it so that their stomach ailments will be taken care of. So this was like a very, very interesting and very funny story behind oil. That whole petroleum industry, which is like a multi-billion-dollar industry now, actually started with this fellow trying to sell it as a skin ointment. Is it's very, very funny for me. So I thought I can share that with you. So it started from there, and then they realized slowly that, not slowly, immediately they realized there's a big potential for it to be, sold as lighting oil. Then you won't believe that before that, they were really I think India probably we were using castor oil and all kinds of vegetable-based oils for lighting lamps and stuff like that. And in Western countries, especially when probably they did not, in the Scandinavian region or not, much north of, the northern hemisphere, those countries, Europe, northern Europe countries, they were using whale oil. Basically, they were really killing off, and some of the whale species are extinct. Those even before 1900s itself. So that started around 1600 or even before that, and for some 500 years they were killing off all those big whales for oil. And then those industries are those relics are still there actually in some of the islands in the northern hemisphere. So that is what they were doing, and they tried to. In one way, it is okay because I'm sure the whale population would have been killed off completely otherwise. And then they got this oil, and then slowly started replacing that. And in 1900s, then invention of automobile happened, and then mass production started, right? So in 1913, if you see this, Ford, of course, I know you, I'm sure you all know the story of the automobile. Ford started, and then Carl Benz started with the first petrol-powered car in 1885. So this is the era in which lot of changes were happening. So unless petrol was found or discovered, you wouldn't have had automobile industry. So that is what I mean by sustainable development. You wouldn't have had any car or any kind of transportation, what we take for granted now, unless some kind of fuel was there, right? So that way, oil really like kicked off this automobile revolution, literally. Then better quality fuels they wanted, because otherwise they were not running really nicely, and then they led to catalytic cracking. Initially they were trying to put as such oil, crude oil. I don't know how many of you know that crude oil is a mixture of large variety of hydrocarbons. So we can't really use that. It just vaccinate. It will go and choke your plugs and all that. So you cannot really use it. And then because of that, 1937 catalytic cracking. So one of the earliest mass industrial scale heterogeneous catalysis was used in this, and this catalyst is used even today. And then afterwards, what I would say is that Haber process, I'm sure you all know, ammonia production, iron oxide catalyst was used. And recently, there was a Nobel Prize for that. 1970s, polymer industry started, another revolution, automobile revolution, and then afterwards it is a polymer industry revolution. A new catalyst also started developing. And now what we do is now see, we need to take it now. Catalysis has to, or chemistry has to take care of all these pollutions which started happening from 1900s due to chemistry. Basically, chemistry right now, or you people who are working in chemistry, you will be working in chemistry later on, your next generation. So you will have to take care of the pollution which was formed by chemistry from I don't know, last 100 years. That is the problem. So oil and petrochemical industry has driven development, but not sustainably, is what I would all think. But then I don't think we would have been where we are right now without this oil and petrochemicals industry. But then right now we can look at it in a sustainable way. So early industrial catalysis, there is like some of the main things people were using. So I will just skip this. And another thing is, I would also say that heterogeneous catalysis is my field actually, can be considered as an oldest form of nanotechnology. So everybody says nanotechnology, nanomaterials and all that. But catalysis has been doing nanotechnology from, you can see this year, 1925, it's a 1995 paper, because they did not call it nano, because it is very practical, catalysis is a very practical science, it is done in industries. So this Professor Taylor really understood that it is a surface of a granule. It's a small, he called it as a granule, a small particle. So surface is very active, and there will be atoms which are not connected to anything, so that will be more active. Like that, he started kind of hypothesizing, and then he had contributed a lot into this kind of catalysis, nickel-based catalysis. So this is one of the earliest mention of a nanoparticle or a granule, and why surface chemistry of a nanoparticle will be different from that of a bulk. So this is also very interesting to look at. And now heterogeneous catalysis is present everywhere. You look at petroleum industry, pollution abating, green chemistry. Green chemistry, one of the principles itself is reduction, principles of green chemistry, which stipulates reduction in byproducts, increase in atom efficiency, right? It has to be brought about by catalysts only. So that way, heterogeneous catalysis is part of your daily life now. For example, one of the main examples would be catalytic converter. You look at the catalytic converter, it is basically a solid, something of the sort. You can see that that solid particle, some component in which heterogeneous catalysts are wash coated, we call it. And then it does all the reactions, like it does a three-way reduction to get rid of NOx. then clean exhaust comes out. And then, of course, it also gets rid of carbon monoxide, unburnt hydrocarbons, etc. So this is how. So all cars anywhere in the world will have this catalytic converter. So you can also have a look. It is just at the inlet of your exhaust. This is exactly where. Yeah. So you can have a look at it. So it's one of the omnipresent. It is every day with you. This catalytic converter. This is one of the very interesting examples. And how does catalysis happen on nanoparticles, right? So, for example, this is a platinum alumina, as I said earlier. It's a platinum on alumina. It is a simple method, simple way of making. It is nothing very complicated. It's a simple nanoparticle. You can see it's around 10 to 15 nanometer of particle is sitting on top of a bigger alumina particle. Very simple. But then, nanoparticles, why it can have many shapes. I don't know whether you are taught maybe BSc, I'm not very sure. So this is how your solid crystalline particles look like, right? Whether it is a nano particle or big particle, whatever it is, like minerals, metals, all those things will have this kind of structures. So this is how the atoms are placed. So you can see that depending on the shape and the size of the particle, you will have different types of atoms, like different numbers of atoms, different connectivity of atoms on the surface. So this kind of change the heterogeneous catalysis. For example, if you look at here, it's a cube, right? And then if you can just cut these corners, all the corners, you keep cutting that corner, it becomes a cubo-octahedron. So this cubo-octahedron is one of the most prevalent nanoparticle shapes, especially when it comes to metals and metal oxides. And then you keep on cutting, it becomes octahedron. But in a cube, you will see this plane more. But in an octahedron, you will see this plane more. This is the shape. So because of this, there will be a change in the activity. So that is what this shows. So change in the activity. And I will just show an animation. So for example, this is a simple support. This blue, let us assume that to be alumina, in oxide support. And then you put platinum on top of it. So orange, let us assume it to be a platinum nanoparticle, right? And it will not be like a nicely spherical particle. It will be like a hemispherical particle, because when you make it, it will just go sit on top of the alumina. Now you see, this is a carbon monoxide coming and reacting. I'll just go back and it's what I'm showing here is a carbon monoxide plus oxygen. It's a simple oxidation reaction. So that carbon monoxide and oxygen will come and adsorb on top of it. CO2 will form and desorb from that. So that is a simple reaction as I've shown here. So CO plus half oxygen forming this. And then in here, the reaction, when the reaction proceeds, there are many ways of that reaction to happen. And this reaction, adsorption, desorption, all that also will depend on the size of the particle as well as which plane it is coming in and attaching to. So this is how this changes. And another example which Atul will be very, very familiar with, because I've taken it from his work. So it is a cinnamaldehyde hydrogenation. So it can form many different products. So which product do you want? So if the cinnamaldehyde comes and sits like this, then it can get hydrogenated here, 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 everywhere. But if it comes and sits like this, then only aldehyde will get hydrogenated or oxygenated or whatever. So that is the difference. So this is this way of adsorption depends on the way in which you make the particles, what is there on the particle size, what is the size of the particle, and like in the previous slide I showed what kind of atoms are exposed. So these are the many different things. So for example, here you can see in the table, you can see that different particles, different planes, 1, 1, 1, 1, 0, these are called Miller indices. And this you will learn in your solid state chemistry or in organic chemistry courses if it is part of your curriculum. And then you know how all these CO adsorption energies, CC adsorption energies. So depending on that, all these reaction kinetics also will change. Depending on that, your energy changes, hence the reaction coordinate also changes. So this is how nanoparticles help in heterogeneous catalysis. So this is our 10 commandments, I would say, or only one commandment we have in heterogeneous catalysis. is that it all depends on the size and shape of the active metal or active metal oxide particles. So this is the premise under which we work in catalysis. And now we will go in quickly into petrochemicals. Like I said earlier, we talked a little bit about how oil came about, and then how oil is, of course, from oil only petrochemicals. I don't know whether you can see this everything properly, but you can always go and see the sites that you will understand it better. But at least till here, I'm sure you can see. So you see coal has to, it can come, you can even start making, through gasification, can go into methanol economy is important. We will talk about that a bit later. Nuclear, forget about, we will not talk about it. Biofuels and renewables is a very nice thing. I'm sure, somebody will talk about that, not me. Crude oil and natural gas is what, right now we have enough. And that is what is the most polluting also. So we are using it, but we need to find out ways of using it better. So crude oil distillation and how refinery gases will form all these things. This is LPG. In the form of LPG, it comes to your house. But before all these, there are a lot of polluting ways of cleaning it up. And all these gases, ethane goes into ethylene goes into polyethylene, and then becomes plastic. So every smallest part of your crude oil is used somewhere. There's nothing we lose. Earlier, people used to flare gases. Even that we don't do anymore, because gas also you're collecting and then using it, because methane also can be value added a lot. So this is how your petrochemical industry works. And you can see that every day-to-day life, how much, if tomorrow, if somebody says that there's no petrol coming, it is not just your car which is going to get affected. So we always have a feeling, no petrol means, crude oil means we will not be able to travel. But no, we will not be able to live in the way in which we are living right now. We will not be able to use not even half, 90% of the appliances which we use right now, because no plastic will be there. A lot of things will not be there. So this is the permeation of petrochemicals in our everyday life. How much we are dependent on petrochemicals is what. So to keep this comfort more, we need to keep the oil also more, or find out better ways of using non-polluting ways of using oil to produce the rest of the commodity items. So now how did petrochemical industry come about? So I would think I've just given a past, present and future scenario. So the first it started off with the Haber-Bosch process with iron oxide. And then basic cracking process, as I said earlier, with platinum alumina, they wanted to put the oil, they understood that oil can be put in cars to run the cars, or even burn for lighting. But then they realized that it is not very clean. So you needed to clean that crude oil. So that is why necessity is the mother of inventions, people say, right? So exactly what was happening. So they came about with the cracking process, again catalyst, and then Ziegler-Natta afterwards polymers. Then emerging market. This, I think you can forget about it. We are not talking about the markets and all here. Then now currently what is happening is we are working with all this, because ammonia is still the biggest industry. Ammonia is still the most polluting industry and most energy intensive industry. But still we cannot live without ammonia, right? Because our farmers depend on the fertilizer. So if the farmers reduce the fertilizer usage, maybe we can reduce the ammonia production. So that is a completely different, it goes into politics. So let us not go there. Now what we are having is a stricter environmental regulation, right? Now we cannot just like that put any petrol, any level of purification to our thing. We have like Bharat 6, you have heard of that, right? So BS 4, BS 6 and all that. So from 4 directly we jumped into 6 right now. So what it means is that your some of the, like for example, sulfur content should be below a certain ppm. So like that. And then globalization became. So globalization, mainly what has happened is that we have access to, and other countries have access to our market, right? So right now, we are not importing much from China, but maybe like 2 years back, almost everything was coming from China. So that kind of a globalization also is there. So we need to be more careful about how we approach problems. And the petrochemicals from other feedstocks. but like for example, plastic. Can we make plastic, but not from oil, from bioresources? It is possible. It is possible that you can make a PET, replacements from glucose. So those kind of things we need to be. This is a very, very important and very interesting, field. And then there are many these kind of things. This is like methanol to olefins, because we need olefins, right? Olefins means alkenes, double bond. So we need a double bond to make then chain and make a polymer. So olefins are very important. So methanol, can we have a platform chemical like methanol, which can be made from somewhere else, and then convert that into olefin, and then olefin to or gas to liquid. This is also more or less like that, like gasification, gas to liquid, for example, syngas to methanol, like that we need to think of. And then coal to liquid, that also is very important. Like I showed in the previous slide, that coal can be gasified into syngas, and then that syngas can be converted into methanol, right? So, and many like Fischer-Tropsch and all that, and shale gas, I will that. So that is what is happening right now, presently. And now in the future, what are we going to do? So shale gas is one of the things from ground directly you take ethane is what shale gas is. A little bit of methane also will be there, and the US has a lot of things. As usual, India does not have any of these resources naturally. So we will have to really depend on somebody or other, but still we can do something. And in the future, shale ethane will be a surplus. And shorter routes from oil to petrochemical, because we'll skip this for now. And methane directly, can we make it into higher alkanes, because you may get methane from oil. And CO2 utilization. So this is one of the most important things for future. So whatever process, most of these processes produce a lot of CO2. So can we make, do CO2 utilization? Mitigation is more important, but if you can utilize it, is even better. Then alternate feedstocks, sustainable methods. So these are going to be the future. So basically, you students should be looking at this part. This is what. So we are working on this and maybe polluting the environment, but you will have to take care of that. So alternate feedstocks for petrochemicals. Now in Indian scenario, why do we really need that, right? So now you all must have heard that we are going to have a lot of electric mobility and all that. So it was 2025 was the limit, but then I think that then afterwards they moved into 2030. So 2030, and then just recently in 2017 they said it is not even possible in 2030. You will have to wait till 2047. So 2047, and also even for a person like me, it is like who knows what is going to happen at that time. So this kind of thing is happening. I was also actually thinking that maybe in 2 years' time we will have a lot of electric vehicles. I was even planning to buy my first electric vehicle and all that, but then nothing is happening. Maybe because the battery technology we will have to import, and that is not going to be sustainable. Maybe because of that, it is really not going off well. But just recently only, you must have seen that oil prices are coming back up. It was very cheap for some time, but then now it is coming back up. I don't know whether you people really follow this thing in your age. It is like it doesn't really matter. But if you are following, you would have realized that it is coming up. It is slowly increasing. So there are, like, if you look at the reasons, like tension in Syria, sanction to Iran, unrest in Venezuela. So, for me, all these countries are all like, we don't really have a say in any of their politics, right? Even in politics itself, we don't have much of a say. So forget about these things. So what do we do if there's a tension in Syria? So these are completely external factors. So we don't have a control over petrol price. First thing is that is what we should understand. And second thing is that if we finally move completely into electric mobility, right, then there will be less interest on oil refining, right? Then we don't really need oil. We are completely dependent on this. So basically what we can do is we can burn oil and produce electricity and then charge our car. But is that a sustainable way of doing it? I think it is not a sustainable way of doing it, right? How can you burn oil? It is the same only. So what are you doing by making electric mobility? So that is not the way. So you will have to make electricity from renewable sources only for that purpose. So Then we have an incentive for alternate feedstocks. Like where are we going to get the petrochemicals? You saw that petrochemicals are from crude oil, right? Now crude oil is either finished or nobody wants to it becomes too expensive. Then what do we do? So then we need alternate feedstocks. And for example, for India, we have even another one reason, because we don't produce oil. We have to always depend on outside countries. We have very limited, very less oil production. So we have to always depend on outside parties. So let us not do that. So I think we have a very good incentive for alternate feedstocks. So now what are the alternate feedstocks we can use? All these things I talked about earlier, like methanol to olefin, like ethylene propylene. And this was proposed in 1977. As usual, largest commercial producer is China. And then what you need to understand is that they will produce all these things and they will just dump it in much cheaper to India also. So we will have to make it in a sustainable way, a cheaper way, and compete in a global way. That is what globalization becomes one of the most important things. Because if we don't compete globally, we will not be able to. We cannot shut ourselves in our country within the borders and then make everything. It is not possible. We have to be competitive with the others. So these are some of the industries which are doing that. And coal to liquid fuels, direct coal liquefaction. Again, China is only a company who's making it, but then it produces a lot of pollution. So India is also now coming to that, but hopefully we will take care of the pollution much better. Indirect gasification and conversion to methanol or FT fuels, again by in South Africa by Sasol. So these are very famous petrochemical companies. And I mean, you may not, I don't know whether you are aware of, but Sasol and Mobil is one of the zeolite making. First zeolites were founded by Mobil, and natural gas to liquid fuels through FT. FT is a Fischer-Tropsch. So these are the ways in which we can really do, find some alternate feedstocks. Now we will come to CO2. So CO2 in India has a very specific, we cannot really look at other countries and make our decisions. So CO2 in India originates from power generation. You can see that nearly 65% of our power is generated by burning coal. Like I said earlier, hydro is only this much, let us say 20%. 20%, it is because maybe in northern states it is possible because you have glacier meltwater. In other parts, I think it's not very possible. In Maharashtra also we have some dams which are good, but then the frequency of power generation is less. And to put everything together, this is nothing compared to what we generate from coal. And you can see that coal, when you when you burn coal, you don't have a choice but to make CO2. Whatever you do, however clean you produce it, what you can avoid making is soot. So if you improve your technology, you will produce less soot. That means carbon particles may not come out, but CO2 will surely come out. There's no doubt about that. You can only make it more efficient. For let us say 1 kilowatt of power, maybe 1 ton of CO2 is produced. Then that efficiency can be reduced, or maybe 0.5 ton is produced, but still CO2 will be produced. And a lot of other sources are there, like industrial activity. Cement plant is one of the main things. Iron, steel, like I said earlier, chemicals, everything. So quite a lot of CO2 is produced by that. And now look at the captive CO2. Captive CO2 means that what is the CO2 which we can really utilize. For example, a vehicle which uses CO2, which produces CO2 in the tail. But can we really use? How you do put a bag and collect the CO2 and then take it and all that is not possible, right? So these are for example, vehicular pollution, CO2 and all that, we cannot really do much about it. You can reduce its sulfur, SOx, NOx and all that by changing it. And carbon, like I said, soot particles also can be controlled. But never CO2 from a vehicular thing. But captive CO2, especially from thermal power plants, we can really utilize. So coal combustion accounts for nearly 40% of CO2 emission globally. And India depends heavily on coal for power generation, as I said earlier. And this is one of the things which I talked about in the sense of efficiency. Electricity emission intensity means like how much of CO2 is produced per kilowatt hour, right? So you look at India. India is 926 grams of CO2 for 1 kilowatt hour of electricity generated. Look at the global average. It's only 533. We are almost double that of global average. So that means that our methods of coal power plants is extremely inefficient, right? We are producing for 1 unit of electricity, we are producing double that of carbon dioxide compared to, for example, America or Europe. So that is not a good thing. So I think that is one of the focuses right now, that to improve the efficiency, and maybe we will get to be somewhere near 500 very soon. And if you look at this chart, you can see that it is not, now it is going up very drastically. You see that? So it is not very much because it was under government control and a lot of issues were there. And suddenly when it is freed up for private players also, it starts increasing. And then it goes exponentially. And then you can see that announced is like around 2025 also, there are announced things, but slowly it will surely come down. But you look at the annual emissions of gigatons of CO2, it is going to drastically increase, right? So we don't have, and then in India, we don't really have a choice, but we have a lot of coal. There's no doubt about that. Our coal, quantity is quite high. No issues. We should use our coal, but our coal has a lot of ash in it. Our coal is not as efficient or as good quality as in a lot of other parts of the world. But then that comes on to scientists, right? Like you and I, we have to figure out ways of using this dirty coal in a much better way. So one of the reasons why this electricity emission density is very high is because of that, because the quality of the coal is very bad. So that is one of the reasons. So anyway, whatever it is, CO2 utilization is a must. So now what can we do about it? I will not go too much into the chemistry part of it, because I would like you guys to get an idea about what are the things which we can do rather than the nitty-gritties of the things, even though I will touch upon it. So let us say you have CO2, right? And methane also in some of the places, like in biogas, for example, you have CO2 and methane, right? Now we have a lot of biogas and we have to convert it into not a biomass, waste biomass, waste, organic waste, city waste, everything is there. So that whatever comes out of will have CO2 and methane in that. So this is a biogas. Or else you can have CO2 and hydrogen, which can be either from renewable hydrogen by photocatalysis. Even though this is a very inefficient process right now, I'm hoping that someday, maybe 50 years down the lane or 20 years down the lane, somebody will have a much better way of making hydrogen just by using solar light and nothing else. So now what you can do is, if you have CO2 and methane together, as in a biogas, you can do something called CO2 reforming, okay? And then that can produce syngas. And I'm hoping that you know what syngas is. It is a mixture of carbon monoxide and hydrogen, and that can be converted into methanol, dimethyl ether, which is also an alternate fuel. Then FT fuels. FT fuel means alkanes and other larger chain alkanes. Then another thing what you can do is you can use CO2 and use this hydrogen, which is renewably produced, and then directly hydrogenate it into methanol. And then that can be dehydrated to DME. Or else you can use directly solar and CO2 plus hydrogen in presence of solar, and then directly make methanol. Another thing what you can do is you can we have somebody who's looking at a very, very fancy catalysis and trying to do CO2. This CO2 plus hydrogenation is a very high pressure reaction. I will come to that later. But he's trying to make it in an ambient condition. So trying to reduce that into CO. CO, then you can mix it with hydrogen and then make other like methanol or other platform chemicals. Or else you can use something called RWGS. It's a process called reverse water gas shift. Okay. So that also is one of the processes in which CO2 plus hydrogen can be converted into CO and water. So these are the things which we can really do. And this is what we will be talking about from now. So now CO2 utilization, bulk chemical into methanol. Now, why do we need methanol, right? So what is, why is methanol so important? I don't know whether you have heard of something called methanol economy. So that is something which India is looking for. methanol economy, increase of the methanol, mix methanol with our fuel. Like you go, even now also you go to a petrol pump, you are supposed to have 5% of ethanol mixing. I don't know whether they're really doing it, but then that can be increased to 10% and plus 10% methanol mixing. That means that in your import, you are reducing nearly 20% of your import of the gasoline. So these are the things is called a methanol economy. So some newspaper items and all that. So you have a feeling that, okay, we are going to get into some methanol economy. And if in that case, then we expect exponential growth of methanol is what we expect, right? Are we ready? Of course not. In global scenario, you can see that there are like people who are companies, European companies and all that, huge amount they are making. And we are also making a little bit of the thing, and our demand is even more than 2 million. This MMT means million metric ton. So, but our capacity is only 0.47. And out of the 0.47 MMT capacity, we produce only 0.2. So where is 0.2 and where is 90, which is a global? And most of it is like produced from some 3 or 4 companies and by China and a few European countries and America. And now where are we from 90 and 0.2? Even that is even not even taking care of our own things. So we have started importing 2 MMT, and from where? China. So when we start hating China, we should also remember that we are getting a lot of items from China. So even methanol we are getting from China. Methanol, which forms the basis of most of our industries, we are getting from China. So we are really not ready for this. So now what can we do about it? Currently methanol is produced how? It is from reforming and gasification. So reforming means, like I said earlier, right? You can use natural gas, ethanol, almost anything you can use as a thing. And coal is used mostly in China. You can use biomass. You can, only thing is energy intensive. You use water and then 950 degrees centigrade, 30 bar steam pressure. You use some kind of a simple catalyst like this, and then you produce syngas. Syngas is like CO and hydrogen, like I said earlier, with a specific ratio. And then this is the catalyst which is usually used, and the condition is around 300 degrees centigrade and 30 to 120 bar of the reaction. And then you make a methanol, which is purified to a fuel grade. So this is the simple way of making it. And this is, methanol, like 90 million tons of methanol is made every day. So this is how it is done. And what are the reactions involved in it? You can forget about the second part. You just concentrate on these reactions. The CO2, CO plus CO2 plus hydrogen is what is syngas. So you have CO2 reacting with hydrogen to form methanol, CO reacting with hydrogen to form methanol, and CO2 plus hydrogen forming CO. So this is one of the, all 3 reactions will happen in all your methanol synthesis reaction. And it's an exothermic reaction and maximum conversion at low temperature and high pressure. I think this is one question I always ask everybody about Le Chatelier's principle. It's an equilibrium reaction, right? So how Le Chatelier's principle affects this? So I think this is some exercise you can also try to do. And you can see that at low temperature and high pressure, it works very well. So that is one of the reasons why we should be doing that. You can forget about all this. And then if you look at the mechanism, this is normally the catalyst which is used, copper, zinc, aluminum. It is a simple catalyst. You have copper oxide, zinc oxide, aluminum oxide, mixed oxide. It is called a mixed oxide. But then, of course, all mixed oxides don't work. A specific way only it works. And then a CO2-CO redox system is involved, highly dependent on the ratio. And also, one of the reasons why it is important is that theoretical and isotope studies have suggested that CO2 also gets hydrogenated, and only 1/3 of methanol is actually coming from CO. It's mostly coming from CO2. So that is actually a very important thing to understand. But then you will start thinking, right? If CO2 is what is getting hydrogenated, why not you do it directly from CO2? So that is where we are going. But higher concentrations of CO2 is detrimental due to water-induced deactivation. So these are some of the ways in which like people study this. You can look at these papers if it's available. What are the intermediates which form? So CO2 gets adsorbed, reduces energy, then the CO2 adsorbed forms, and then some kind of a formic acid kind of a formate kind of a intermediate forms. So like that. So like huge amount of studies and brain goes into understanding these kind of mechanisms. But then, of course, it has not affected much about the catalyst, because catalyst is more or less the same we are using for past 100 years. Now, if that, like I said earlier, if CO2 is what is getting hydrogenated and forming the methanol, then why not use CO2? Why you have to burn natural gas, gasify natural gas, make syngas, and then produce methanol? Instead of that, why not use your CO2, which is coming from your coal power plant anyway? Because anyway, we need electricity. So anyway, we are going to burn coal. So why not use that CO2 and make methanol? So that is where CO2 hydrogenation will become very, very crucial for our country as well as for science in general. Because now let us compare syngas conversion and CO2 generation, hydrogenation for methanol synthesis. The syngas production is highly CO2 emitting, which is around 25 tons of hydrogen for 8 tons of CO2 is produced per ton of S2. So that is also very, very, very highly CO2 emitting. And then capital intensive, 60% of methanol plant is actually syngas production, and high pressure process, which is okay, 50 to 120 bar, that is okay. And established only advantages, this is a disadvantage, this is an advantage. Established process, because for, like I said, more than 50, 60 years it has been going on. So everybody knows how to work with it and people just stick with it. You don't want to change anything. But in CO2 hydrogenation, the advantage is it uses waste CO2, like I said, from power plant or industry or wherever, and avoid energy intensive syngas production. The 60% of methanol plant that can be avoided. It can be completely renewable, provided hydrogen is produced from renewable sources, like I said. So renewable sources means what are the options for us? You can think about that. One option is that, like I said earlier, you can take water, you put a catalyst, like a photocatalyst, expose it to sunlight, break water into hydrogen and oxygen, and use that hydrogen. Very simply said, but very difficult, but still, okay, some point it may work. Second thing, what you can do right now also, which is possible, we have very good infrastructure of photovoltaic cells, right? I'm sure, your home also roof, in my society and all that, we have rooftop solar. So it is a very, the government is really, giving a lot of incentives for people to produce solar electricity. So photovoltaic cell is there. Then you take that electricity and electrolytically split water. So water splitting not by photon energy, by electron energy. So that way you will not be using the any polluting method of doing so. That kind of a thing is even now possible. So one of the biggest disadvantage of this process is actually hydrogen sourcing, because we don't have hydrogen. Hydrogen is an expensive gas for us in India. And if you start producing hydrogen from fossil fuel by gasification or something, it doesn't, no environmental benefit, right? Might as well send out CO2 from the power plant instead of making hydrogen and doing all these things. So this is the comparison of that. So in my view, we have quite a few advantages of CO2 hydrogenation, which we should really look at. And I think I will just skip this. Some of the breakthrough researches I will just quickly go through, because some of these things are becoming technologies, and then maybe tomorrow, tomorrow in the sense like in few years, maybe you will see methanol production from these kind of technologies. So this is using again a simple. So heterogeneous catalysis, I like it because the catalysts are very simple, nothing like very complicated like homogeneous catalysis kind of structures, and nothing is there. Very simple. It is an indium oxide and zirconium oxide, a very simple thing, but it does wonders in converting CO2 to methanol. Another breakthrough research is this. So they have found out through theoretical studies, there's something called volcano plots. If I think MSc students, maybe you can have a look at these kind of papers. So they have done this volcano plot and figured out that something nickel gallium alloy is very close to the conventional copper zinc activity, and then they made the catches and actually it worked. So that is one of the breakthroughs. And one more breakthrough is there, which I haven't put it here. I think I forgot. Is from one of our earlier students. I think Atul probably know. His name also is Atul. He is working in a Japanese with a Japanese group, and they also have come up with a very high pressure but very active catalyst for this thing. And now you can ask, okay, like a lot of studies are being done, and then what is happening in industry? Is industry interested in doing this? This is one of the things which we always ask. Like you do a lot of basic studies, everything is good, okay, 10, 15 years you work, but afterwards also if it's not getting commercialized, then that it is not, you will have to change something to make it more commercially successful. So Mitsui Chemicals is doing that using their own hydrogen, and they are supposed, but then afterwards I have not heard anything. They are supposed to have put a commercial plant in 2016, but no news afterwards. So I'm not very sure exactly how that is panning out. But this is how things are going. And then this is working out very well. This is in Iceland, and they have geothermal sources. They use a heat from ground, and they use that for making hydrogen, and then use that from electricity, and then they use that electricity for making hydrogen by water electrolysis. And then this is going very well. And then apparently very recently they have started even using this methanol to run Volvo buses and all that in that area. So this is quite good. So maybe what I feel is that you can always have a it is quite possible that when you see people, other places, people are putting up plants and then using that methanol for running their vehicles and all that. So there's a hope in this technology. So this is like a successful technology, I would say. And this is, I think, I'm sure you would have heard of Professor George Olah. So this plant also is put up on to respect him. Actually, he just passed away the last year or 2 years back. Otherwise, he was a proponent of methanol economy. So he was saying that we should come out of this gasoline and all that and use methanol and then capture the CO2 and then recycle back into the thing. So this is one of the things. If you have this kind of access to these kind of papers, you can have a look. I've given all the references in the slide, so you can have a look at the references. So Atul, if I'm going over time, you can stop me anytime. Okay. Okay. I'm visible, right? I'm audible, right, Atul?
Hello.
Yes.
Yes, ma'am, you are audible, ma'am. You can continue, ma'am.
Okay, okay. For a moment, I was like a bit. I got a bit worried. Yeah.
Right. Okay.
Yeah, it's okay. I'm still in the same thing. Only something happened. Yeah. So now, if you look at this, it is the carbon capture. Yeah. Sorry, Atul. I was just asking, am I going over time?
No, it's okay, ma'am. We have no problem.
Okay. Okay.
We have time. No problem.
Then I will continue. So if you look at this carbon capture and recycling, then you can look at atmospheric carbon dioxide you can take, and then capture that, or even from point sources you can take atmospheric carbon dioxide you can take, or from the vehicles you can take, from wherever, and then you can make do that and catalytic or electrochemical CO2 reduction transformations to CO2 DME, and then you can make methanol and DME, and then use that for other hydrocarbons and products, like I said earlier, methanol to olefins. That kind of process, and then all other petrochemicals can be made, and then you can use that for running your vehicles, and like that. So it becomes like a circle, and then you can use hydrogen generation from water. You can use any of these things, like geothermal is what they have used in Iceland. You have tidal electricity, atom. This nobody's sure. The people fight among each other, like nuclear energy is clean or not. It's something which I don't want to get into. But solar is clean, wind is clean, hydro is clean. So you can use all electricity to produce hydrogen and use it for converting CO2. So it goes in a cycle. So even if your vehicles produce a CO2, you can always take that CO2 from atmosphere and start making. So this is the ideal situation. It's an utopian idea actually. So that everything, so we don't increase even one atom of carbon dioxide from the current situation. So we keep on recycling. It is what Professor Olah's submission was. And now we'll go into the next thing I was talking about. This is something which even CO2 to methanol also we are working on, like in a very basic thing, not the technology development or anything. But this is something, this CO2 reforming, as I said earlier, is something which we have been working for quite a long time. And then now we are working in a, like a pilot scale. We are trying to scale up the technology and then trying to bring in industries and, that kind of stage we are in right now. So dry reforming means methane and CO2. Like I said earlier, if you remember, I said syngas is produced from natural gas or any form of reforming. You can use a lot of things for reforming. That reaction is called reforming, or SRM they call it, steam reforming of methane. So what they do, you take methane, you add steam at high temperature and high pressure, and then you produce CO and H2. So this is the ratio. This is not the ratio. Actually, it should be CO plus 2H2 when you do it with the steam. And instead of steam, now you use CO2. So that is why it's called dry reforming. That means instead of steam, which is water, you are using CO2. So it is dry. So it is dry reforming. But the problem is that it produces 1:1 CO and H2. And for methanol production, you need 1:2. So that is one problem, but then there are many ways of getting out of it. So advantage is 2 greenhouse gases can be utilized for this purpose. And another thing is that we have a lot of biomass. I think I don't have to tell you guys, right? I think you people must be like suffering from biomass in your state, isn't it? Like you have a lot of biomass and then you don't really have a choice but to burn it is what the problem is. So now can we utilize those biomass? And you take all that and then convert that into gasify. Gasifiers also, I'm sure it's available, but what people do is normally put everything together and co-generate electricity. You make electricity out of it by running a turbine and all that. But instead of that, you can gasify this into biogas, that is a mixture of methane and CO2. Then you can directly, from your crop waste, you can directly go into methanol, which you can put it in your tractor. So that is another one cycle which we can talk about. So H2 by CO is apt for downstream in the sense like you need to take, by adding a little bit of steam, you can make it to 2, and one is enough for ST, DMA synthesis and all that. But there are a lot of challenges. I will not go into the details of all these things. Like there are carbon formation. One of the, nightmares of a catalyst or catalysis person would be coke formation, because, like when we pray and hope whenever we load a new catalyst, that hope it doesn't form carbon. But, most of the time it forms carbon. So one of the devils of this catalysis community is that we need to somehow manage to avoid this reactions. So I will keep because this is some of the results we have, and of course in our place in NCL we always do like a longer time on stream and all that to see how far it will go. So we have developed a new type of catalyst. Which is a very less like carbon formation, which is only around 4% against 40% in the conventional catalyst. So that is what we have. This is the Raman spectrum. So Raman's spectroscopy. So like from Raman you can figure out different bands of carbon and all that. So that is how we find out. And you add little bit of water into that. It is called bioreforming. You add little bit of oxygen also into it. It is called dry reforming. And then what you end up doing is you increase the ratio of CO and hydrogen. So that is something H2 by CO ratio we call it. So it is usually 1 that can be increased all the way up to 2 by adding all these things. So that is one of the ways in which we do that. And now again, like last time, what is industry's perspective on that? And are industries interested, or are industries interested in investing in that? So actually, it is this is a big company. Linde is a big company, gas company. It is. They, you may see them transporting gases like oxygen and nitrogen, liquid nitrogen, and all those things. You may have seen this name in some of the trucks which pass through. You can look for that. So this guy is a big, huge company. It's a German company, and they have put up a plant in Munich for this with the BASF catalyst and all that. So this is a very interesting thing. So what they are saying is that if you reduce the CO2 emission by around 1 lakh tons every year, based on a dimethyl ether production plant with an annual capacity of about 1 million tons. So if you have this kind of thing, then this kind of DME plants based on this, dry reforming, then so much of CO2 can be reduced. So in our country, it comes into so much of smoke can be reduced from stubble burning. Instead of that, you can convert that into gas and then use that gas for making the thing. So even our air pollution issues also can be probably addressed to a large extent. And these are not things which I am working on, but some of my colleagues are. So I will just give you a quick thing. So if any of you have interest in that, or maybe small projects or something you want to carry out, then you can really do any of these things for that matter. So this is a very close to my heart. I really like this way. Like CO2 is there, and you have heard of polycarbonates, right? Polycarbonates we use almost every day in our life. Most of the roofing sheets are polycarbonates. So they are made from polyurethane, and then also polyurethane also for packaging. It's a huge industry. So now it is actually made from a very, very polluting, very poisonous, like isocyanate and all that they use in that process. So if we can use polyols and poly and carbon dioxide directly to make this polycarbonate, then I think a lot of issues of pollution from polymer industry can be addressed. So this is a very important field, and I wish that a lot of polymer people will be working on this. And then very recently, Ford has said that I think November is one company which started producing it very recently, and in 2016 they started, and this is 2016 May 17. This is the first truck with the polymer going out of it to Ford. So Ford now is making only in US actually. They are, I think this is only probably in Germany. Then they are making all their upholstery, all their internal things using this particular CO2 based polymer, which I thought is a very nice gesture, because their cars of course produce CO2, so but they are using the CO2 to make their own cars, which is a very nice thing. And another thing, this is something which people can do it without much facilities in labs and all that. You can use CO2 for making a lot of fine chemicals, quite a lot of, because this is called CO2 insertion. So you can insert CO2 into certain things or make acids like that. So this also have quite a lot of market actually, but utilization will be less. But still, I think this will be a nice starting point for any of you who's interested in CO2 utilization as such. And some of the work which is happening in NCL, like I said earlier, some fancy catalysis is being done using calcium. So not even like first row transition method. Usually that is the catalyst you see, but he is trying to use calcium-based catalyst for making methanol from CO2. So these are all very, very, very nice and very, very emerging catalysts. And this is like they call it COF, carbon-based organic frameworks. So these are the things, the scientists who are working on it. And again, industry is also interested. A lot of people are working on it. Evonik, Liquid Light, Skyer. So these are the companies who are working on this kind of conversions too. So what I wanted to impress upon the young generation is that these are all not like some fancy, something some people are working on basic. No, it has a commercial potential. It has a potential of coming to your home as some appliance or some product. Like tomorrow when you buy a Ford car, you don't know whether that thing is made from a polycarbonate from CO2, which you yourself have produced, right? So this is how it is a very, very practical, very emerging, but quite potential technologies. So my last slide is is a sad slide actually. Because like I also feel very, very sad when I see all our rivers polluted. I also work with a river cleaning group nearby, and how much ever you clean 1 week, and the next week it goes back to its original thing. I think we as a society, India, as a society, as a people, we kind of tend to litter. We tend to throw things wherever wherever we want to throw. We don't think so much. I think we should change. We should, because all these things lead to pollution. So something, even in organic waste in a river side, we think it is organic, so it is biodegradable. No, but if it is covered with plastic, it produces a lot of methane actually, because it becomes very anaerobic, and it goes into the soil, it becomes anaerobic, and it produces methane. So we don't really think of all this, or we don't really know all these things. Yeah, that thing, of course we do. And then of course, development, like I said earlier, development and pollution should be should it always be together, or we can have development without pollution. I think that is what your generation, I'm talking to the students, I think your generation will have to be very careful, and you people will have to be very active in this area. If you don't say it, then nobody is going to say it, right? Because it is beyond our my generation is is beyond our lifetime, this kind of thing. So I think you will have to take care of it. You will have to be passionate about it, and you will have to question authorities, and you will have to raise your voice when you see something getting polluted. In my hopefully I'm the teachers are not going to scold me later, but I think it is your responsibility, this generation's responsibility to do this. So poor earth is crying and telling you to take care of the mess. So please do that, and I will really thank all this work I've done using funding from government and industry a little bit, and this is my group. And a few of them are really working on CO2. Yeah, a lot of them are working on CO2 related projects on photocatalysis and all that. Okay, then thank you. So I will end here. And if you have any questions, you please ask.
Okay, thank you very much, ma'am, for this enlightened talk. And you really presented a very nice talk. Started from how the oil started being used, and that was really I think that most of us didn't know that people started using oil in that way. Yeah. And now it's the major commodity which we are using. And now the talk is open for questions. I have some questions, ma'am, from student side. They have typed in the chat box. So can I read that? One question is how olefins are alternative way. Maybe she is asking that how olefins can be used as alternative fuels.
No. Olefins are not alternative fuels. Olefins is a base chemical, is a platform chemical, which we need to convert to like ethylene. Ethylene becomes polyethylene, right? Polyethylene terephthalate. So we need, so olefins is that family of compounds which can be made into chains. So that is where most of the ethylene olefins are used. It is not an alternative fuel as such, but we need alternative ways of making olefins for further polymer production. I hope that answers.
Hello.
You can hear me?
Actually, I had some poor connection for some time. So maybe other people were able to listen. Dr. Sandeep?
Yes, Dr. Atul. Yes, ma'am, you have explained it right. Olefins can be an alternative, but not alternative fuels.
Yeah. But olefins will have to be made by alternate ways.
Yeah.
Not if not from petrochemical, what are the other ways of making it? So one of the way of making it is from methanol. Methanol to olefin is a main one of the main things in which China makes olefins still even now, and they make the methanol from coal gasification. So that's all market games which they play. But that also is a very good way of going. So we can also be, what we have more is, of course, we also have quite a lot of coal. So that coal gasification to methanol, to syngas to methanol, methanol to olefins is one way of going. And we can also do CO2 dry reforming using biomass gasification, or biomass gasification, or even biotechnology ways of doing that also is quite good. And that forms syngas, and that syngas can be converted into methanol to olefin.
Yes.
So you don't have to start it from polluting ways of doing it. That is the thing. Yeah.
Yes. And the second question is, can methanol produce from glycerol? One student has asked this. Can methanol be produced from glycerol?
Actually, some reforming of glycerol also is called aqueous phase reforming. So that also is possible. Glycerol is a big side product of our biodiesel. Biodiesel also is a major thing in India right now. So we also produce a lot of glycerol, which is not of the quality to be used in oil and skin cosmetics and all that. So that can be directly reformed into syngas, and then syngas can be converted into methanol. Yeah.
And there is another question from student. I have listened from old people that burning of sarson the oil in India is good. Is there any scientific reason behind it?
Sarson oil means sesame, is it?
That no. Mustard oil.
Mustard oil. I don't have any idea. Because whatever you do, whatever you burn, it finally, whatever it is, it burns into some form of CO2 and all that. But then if there are some kind of volatiles, because I am also a very big fan of natural things. Okay, I also do mosquito repel, and I don't buy all those all good night and all that. I always buy something of this sort, and most of the times they are mixed in some form of oils like this. So some volatiles could be there, which could be maybe good for your sinusitis or something. I mean, don't take my word for it. I don't know. But I feel that some of the old, technologies people were using, our grandmothers, house thing, kitchen, things, they were good. I personally feel that they had some science behind it, and there must be something here also, some kind of volatile which is coming out of it, which is good. Maybe, who knows? So that's something Gurpreet can maybe work on. And as a small project, and find out what is there in that.
And there is a question from another student, from Neha Bansal. Many methods for reduction of CO2 into other hydrocarbon products are energy intensive. Many using catalyst. Could be there cheaper methods for industrial uses? Can you read that in chat box, ma'am?
Yeah.
From Neha Bansal.
Yes. All these are energy intensive processes. There's no doubt whatsoever at all. Because right now, when we are making syngas, the reforming, which is like every other small town in Maharashtra has one reforming unit. Everything, it is like it works at 800 degrees centigrade and around 20 bar pressure. So everything is energy intensive. There is current usage also energy intensive. You don't have a choice but to do it, even after using catalyst. So without using catalyst, even 800 or even that is not possible. No, for these two gases to react, probably you have to go to something like 2000 plasma or something. Then only they will react. You use a catalyst, and especially heterogeneous catalyst, then you bring down the temperature to 800 basically. So everything is energy intensive. There is nothing we can say that it is not energy intensive. All the alternatives, whatever I am talking about, CO2 hydrogenation. CO2 hydrogenation to methanol directly, it works best at 98% conversion at 400 bar. So 400 bar is like, it is not a simple thing. No, the material you need will be very difficult to make. So it is like that. If somewhere you need to compromise. It will be energy intensive. But then the thing is that energy can we give that energy from sunlight, with photovoltaics. So like that, there will be always a compromise. And once I was giving a talk on heterogeneous catalysis, and somebody asked me, all these materials you are talking about, for example, ceria or indium oxide or zirconium oxide, all these are mined, right? You are polluting while mining that material for making your catalyst, you are polluting. So what is the big deal, So, but then that is what I said, it's a compromise. Anyway, right now, one process which is anyway very polluting. So now do we have a lesser polluting alternative, or can we use the same polluting method to use a pollutant, which is CO2, to make something useful? That is all. Instead of venting it out into the atmosphere, can we do something? That is the only thing we can look at. But of course, we always look for methodologies to bring down. If something is working at 20 bar, can we bring it down to at least 5 bar? So these are the things which we work on. That is our research. Yeah. Yeah. Atul, I think has lost, is it?
Yes, I think he has lost connection.
Okay.
Ma'am, I will read one question from the students.
Yeah.
There's one question then, ma'am, these processes will be costly. How can a developing country afford it? Maybe
yeah.
Asking about that.
That's a good question. But you don't think that we are already using these technologies, right? We are already using it. We have quite a lot of. We probably don't make as much as China, but then we still have methanol producing plants. In Mumbai, there is one. In Assam, I have given some of the details. Some few companies are there. So it is a demand. Right now we are importing. So we can afford to buy it from somewhere. We should be able to afford to make it here, right? But then cost effectiveness and all that will come. It is like it is a market, like I said, it's a market game. How do we match the price in which China is selling to us? So that is where all our science and technology stops. We are not able to match that, right? So it is not that we don't have money to put up a plan to produce this. It is nothing like that. But only thing is that we probably won't have the money or the willingness actually to spend on just taking care of pollution. That may not be there. But if we want to make something out of that, I'm sure we will have the money. We can use that, right? Methanol, we can use that. Then it is worth. Right now, also, a lot of companies are interested in using the biomass waste, convert it into syngas, and then into methanol. So that they are interested in, into biogas and then too. So it all depends on what kind of technologies. So that is one of the things which I also think that we cannot just like that blindly follow or imitate Western technologies. We need to see what is available with us. What is our waste? Whatever is the waste in US is not a waste for us, probably. But what is our waste? Our waste is rice straw, right? Rice straw is a huge waste. But nobody in US is going to work on rice straw. Who's going to work on rice straw, right? We have to work on rice straw because that is our waste. So that is why it is nothing to do with affordability. It is all to do with policies, government policies, and our willingness as scientists to work on that. That is my take on that. That's my belief.
There is a question from one of our faculty. Can
you
hear me?
Yes.
Are you doing research on silica nanocomposites for CO2 conversion? And what advantage of silica than other nanoparticles?
Silica as such is not active for this reaction. But silica some active things supported on silica. For example, one of the even the CRI plant which I showed, that their patent also is a copper, zinc, alumina, silica composite. So silica is usually used in heterogeneous catalysis as a support because we think it is an inert thing. But sometimes it is also like I showed, one of my colleagues is working on a homogeneous catalysis using silicon-based homogeneous catalyst. So sometimes they are also quite active. But here for CO2 conversion, as such silica I have never seen, and I don't think it will work. But silica as a composite with other active metals will be working. Okay, thank you.
I think there is no other question. Now, I also have a question.
Yes.
That this coal-based our like use of energy based on coal and petroleum is going to finish within some decades, I hope, because our
but nobody seems to be really knowing exactly when. Nobody seems to be really saying exactly when, even oil companies also. Yeah, but then I also think that it has to finish sometime. Yeah.
So and this problem of the creating pollution by these resources. Hello. Can you hear me, ma'am?
Yes, I can.
So this problem of creating pollution by these resources is not going to last for like eternity. So it's going to like curious whether Indian government is funding on such type of project where like CO2 conversion to chemical.
Yes. Indian government is quite interested. They are supporting, but like I said, more support is there if something useful comes out of it. And finally, all industries, private industries are there who produce, let us say, CO2. So they are also interested in seeing whether some value can be added to that, because they are now vending it out, right? So if they can use it somewhere, they are willing to do it. So it all depends on the value addition we bring to the table. Then it is, and government is supporting, because it may, like you said, because if we keep on doing what we are doing right now, if we keep the status quo, the problem is that the pollution, you expect it to be completely over, then the pollution will not be there. Somehow we can't really think that, because what if it doesn't, it is still there, because shale gas did not exist for a long time. Just recently they found out, because oil is depleting. And shale gas also is very polluting. It's a huge greenhouse gas. So, so we can't really wait for the time when this all resources will be depleted, and then the pollution will not be there. That we may not survive till then. That's the problem.
Yes. So I think there is no other question. And there is a faculty from your alma mater like place, ma'am, IIT Madras. I think he must have some question. Dr. Sandeep Saha. Is he there? Hello, Sandeep Saha, sir. I think I am not able to connect him.
Okay. Yes. Oh, he says voice is disabled by the host.
Oh, let me check. Yes, I am not able to unmute him.
I think university host only can do it. Okay, he has asked me some question. How cost effective these catalysts? Catalysts are not the issue. Catalysts are like most of the catalysts which we are working with, for example, the syngas to methanol catalyst. which is the copper, zinc, aluminum oxide. So it is not at all a problem, because they use tons of this material catalyst for process. And for reforming, it's a nickel-based catalyst, so that also is not very expensive. So catalyst as such is not at all the bottleneck in this kind of process. Huge, big processes, no? These are high volume processes. It is not an issue at all. It's like in fine chemistry, you have like a lot of platinum and all those things involved in it. But even catalytic converter, for example, catalytic converter, almost every other car has that, right? That has not platinum in it. It is a very small amount, but still it has platinum in it. So for pollution control, how much ever money we spend, I think it is not enough. We should not really think about that at all, because the price of clean air, I think it is priceless. Now we are not probably realizing it, but then it is priceless. I hope so. Yeah. Oh, okay, Sandeep. Okay. I finished in 94, so must be like quite long before your time, but okay, good to see. So I think Raman Kaur has asked me, stubble burning is not good, but there is no cost-effective alternative for it. Farmers can do with it. Okay, this is something which I am not an expert in at all. But then what I feel is that this biogas generation, so like I said, so but stubble, how cost effective it is to remove the stubble, that is what I hear, that it is you need to have something to remove the stubble from the earth. So how is that? Rice straw and all that, there are a lot of ways of doing it, but how do you remove the stubble from that, and with so much of soil in it, and you need to clean it for the process? I'm not very sure how cost effective that will be, but one thing what we can do is to use that and gasify it. I use it as a waste, gasify it, use a syngas and make methanol. That is something which we are already working with in the industry. I just hope that something comes out of it. So that can be done, but then the volume is huge because the stubble, it is difficult to compact, and then so much of soil in it. So now what to do with that, I'm not very sure about that. The cost effective part, I'm not very sure. A lot of things you can do with it. One of my colleagues is working actually to convert that into, like completely into polymers, that stubble thing. But again, that do we spend water to clean that? Is that worth doing? Spending water on cleaning that is another one issue. So cost effectiveness, I'm not sure. A lot of things you can do with it though. Okay, so another question is there any utilization of waste generated after coal burning? Coal burning, I don't know what she meant by that.
She means like coal ash. Because after coal burning, we get coal ash.
Yes. Coal ash. It is one of the things which they use in what do you call it? A brick and all that. I always do XRD for that person who comes and takes his coal ash and fly ash, they call it, right? So that, yes, that can be done. That is already being done actually. And there are some government policies also saying that so much has to be utilized in brick formation, something like that also is there. Government policies also are there for helping it. So yes, that is used here. But after burning, because so much of carbon soot comes out and CO2 comes out and CO comes out, then you are not utilizing that. So that is something which we can utilize, and I think it is good. Otherwise, that fly ash people use, but I don't think it's fully utilized. I'm sure there will be like they do some wash is there. I don't remember the name of that. It is called some wash. So that along with that water, they just goes out and they just collect in big ponds. So that is completely degenerates that area. So that is not a good thing. As such, the fly ash which comes out, they can utilize.
Hello?
Yes.
Hello? Now, can you hear me?
Yes, I can.
So actually, I got disconnected for some time, so I can't see any other question in the chat box now. My chat box is totally empty.
Oh, is it?
I
No,
don't.
I can see the chat box without any problem. But this was the last question, and
Okay.
I think lot of people are asking to unmute though.
Yeah, but I think there is some issue from that technical side.
Okay.
So okay,
Chat
ma'am,
box,
and
last
I think
question.
we can then conclude. Thank you very much, ma'am, for your
Thank
nice talk and the interaction with the students. And I thank our administration and IT department for the support, and also faculty members of our department and students for their uh, for their patience and for attending the whole session. And I pass the podium to Dr. Sandeep Kumar, HOD, to say some vote of thanks. Sandeep, sir.
Before that, Atul, can I just say one thing? You can
Yes, ma'am, please.
you can share my email address with the students so that in case they have some questions, they can directly send mail with a copy to you or something like that.
Yes,
No problem.
sure, ma'am, sure. I will do that. Yes, ma'am.
Okay. Thank you, Dr. Atul.
Sandeep, sir.
Thank you, Nandini ma'am. Ma'am, your presentation was very informative, and by the response of the student, they asked so many questions. I can guess this was very much interesting to the students also.
That's good.
The way you presented the different means to deal with the carbon dioxide, the problem which the carbon dioxide poses to our environment, the detrimental effects, that is very much important and informative. And yeah, there is always a answer which is given by science to all the problems. And heterogeneous catalysis, yes, it is very good mean to develop the various catalysts which can deal with the carbon dioxide, which is a very much potent, you can say detrimental for the environment. And I think our students, they get very much benefited from your presentation, and we are very thankful to you, ma'am, and
Thank you.
thankful for accepting our invitation and for such an informative talk. Thank you, ma'am.
Thank you.
Thank you.
Thank you, ma'am.
Thank you.
Okay, ma'am. So
Okay.
I'm ending this meeting. Thank you, ma'am.
Okay. Thank you. Thank you,
Thank
Atul.
you all.
Sandeep,
Thank you.
everybody. All students also, thank you for listening and thank you for this opportunity.
Pradeep ji.